Hello, Vikings. Today we're looking at nuclear chemistry some more. Our objectives are to look at the process of fission and fusion and compare them. We also want to look at some half-life calculations. We're just going to look at the simpler ones. So a little bit of math today. First, though, we're going to go into fission and fusion. Fission itself involves splitting of atoms. Now, remember, we're looking at nuclear chemistry, so we're taking an atom and it's splitting into another type of atom or two different types of atoms, depending on what process is occurring. So you've got that breakdown occurring. So it's not going to happen naturally. This happens generally in our nuclear power plants or a lab somewhere. It's never going to occur in nature. And it happens when we fire neutrons into a nucleus of atoms, causing them to become unstable and split. The downside for fission, we have power plants all over the world now. We have radioactive waste produced, and it takes thousands of years to become harmless. So this is a consideration when using this as a power source. So again, fission, we're splitting atoms. When we look at fusion, it's the opposite. We're combining atoms. Just think of the word fuse. We're putting things together, right? So we're combining two atoms to create a different, larger element. And this is going to take a whole lot of energy. And it's interesting that it occurs naturally. We see this in the stars. And because it is a natural process, we don't have any waste products created. Like we do when we're looking at fission. Okay. So sometimes when you're doing testing, which of course you lucky people won't have to do this year, they will show you an equation and ask you what's going on. So I did want to show you at least one to get you familiar with what they may look like. In the one below, they actually name the isotopes, which may not be familiar to you at all, deuterium. But if you ignore that whole upper line and look just at your equation here at the bottom, you see that you have a hydrogen and another hydrogen, which are being in a reaction which is creating helium. So you should know just from seeing that part of this equation right here that we have a nuclear reaction because there's no other time that an element changes into another element. It only happens during a nuclear process. Again, if you saw an equation like this, you could deduce that it was a fusion reaction because you are putting atoms together. You're not breaking them down. Okay, so we do use nuclear materials probably more than we think. Probably the most familiar for most of us is in nuclear medicine. Almost all of us have had x-rays at the dentist, at the doctor's office. Some of us have had CAT scans or even testing where they put radioactive tracers in your body to have better imaging. And we see nuclear reactors all over our country. And if you do wind up going into the military, you may wind up working on a nuclear sub or something like that. So there are many ways that we can come into contact with the use of nuclear materials. So there are a lot of drawbacks to using nuclear because it's not safe to people and animals in nature. We have the water pollution from the site's nuclear power plants. We also have the radioactive waste that is created by them. We've had some accidents in the past, including Chernobyl, where not only do we lose human life, some areas are destroyed for years, decades sometimes, and you have genetic mutations in some of the children of those who did survive the blast. So the other downside to nuclear is if the accident is large enough, it could lead to some sort of a nuclear winter, which would not be good and which impacts other parts of the world. So the last thing we want to cover today are half-lives, and what exactly is that? Well, when we are looking at nuclear materials, we know that things that are radioactive decay at a certain rate, okay? And so we can get that information from tables, and we can use this info to date things like rocks. Carbon-14, we can use it when we are dating organic material because we can look at the ratio of carbon-14 versus carbon-12. When we are looking at things like rocks, we're going to look at potassium versus argon, or we're going to look at uranium versus lead ratios. Okay, so that will tell us how long it's been there, because how much of it has broken down. So how can we use these numbers, and how much of a population is left if we've had 1 half-life, 2 half-lives, and so on? So it's all very mathematical, and I'm going to show you visually. Here's the actual numbers. At the end of a half-life, we have a half left, and here's why. Let me get out my sketchbook. Come on. There we go. Okay, so looking at this, if I were to draw a rock, I'm going to draw a perfectly round one for illustrative purposes. Okay, so if we have 1 half-life, and let's just say half of this decays, and this is all just for visual. Okay, so this is the decayed part. Okay, that means how much is left after 1 half-life? Half. And you can see that that is over here on my slide. Okay, so then at the end of the second half-life, we would have had another, let's get about half right there, another half decay. So we'll do that. And if you look at this visually and you're thinking about a pizza pie, this is a quarter left. Or if you want to look at it this way, we've had 2 half-lives, which is half times, that doesn't want to work up there, which equals 1/4. And that's exactly what's there. So let's go ahead and do it one more time, okay, just to prove the third half-life. So our first half-life here, then we did half again. Here we are at a quarter. And if we do one more, okay, we'll find that we're at an 1/8. And if you do this mathematically, and I'll do it at the bottom, 3 half-lives, half times half times half, okay, 2 times 2 is 4 times 2 is 8. So we've got 1/8. And that proves what I said on my slide over here. So let me close this out and start a new. Don't want to save that. And we'll open this up just for a few more minutes because we're going to go back to the math. So how can we apply this? Okay, so say we have a 50-gram sample. How much of it would remain after 6 years if the half-life is 3 years? Okay, so how do you determine the amount left? Well, you've got to find 2 things. You have to look at the sample amount that you began with, and you've got to multiply that by the half-life fraction. Okay, and we were looking at the half-life fractions right here. 3 half-lives is an 1/8, and that sort of thing. Okay, so we're going to find that sample amount in this equation. It's 50 grams that we're starting with, and then we would use the half-life fraction. But we can't know what the half-life fraction is unless we determine the number of half-lives. And to do that, we've got to find our total time and divide it by the half-life time. So in our example here, our total time is, let me write it, total time, okay, we've got 6 years, okay, and you see that in the problem, it says how much will remain after 6 years. They're saying that's how much time's passed. Okay, so at the bottom, we're going to divide by the half-life, and it says in the problem the half-life is 3 years. Okay, so if we divide that out, and luckily we can do this one without a calculator, 6 divided by 3 is 2. So we have 2 half-lives that have passed, and we could do it by the division, Or if you're very visual, you could think about it this way. Keep adding 3s, because there's your first half-life. And then if we add our second, we find out we're already at 6. Does that make sense? Okay. So there we go with that. So now we have to solve the of the equation. Okay, let me flip this over for just a second. All right. So the number of half-lives we said was 2, and we worked that out. So what is our half-life fraction? Our half-life fraction, if we've got 2 half-lives, would be half times half. You could even take it off the chart that I had earlier. That's that quarter. Oop, where are we? Okay, and then how much would remain? We said that we had to take what we start with. Get up here. And we started with a 50-gram sample. Okay, and then we are going to multiply by that fraction. Okay, so we should have a quarter of that left. So if we work that out, that's going to be 12.5. Okay, and at the end of that time, 12.5 grams. All right, so it's not too hard. I'm going to show you another, and then I'm going to show you another way to do this. For those of you who may, there's a different way that may help some of you. We all learn a little bit differently. Let me shut that. There we go. All right. If the half-life of 100 grams of radioactive isotope is 8 years, how many grams will remain in 32 years? So we have to calculate the number of half-lives, and we did that last time by taking our total time and dividing it by our half-life time. And in this case, our total time will be 32, and we'll put that up there. Okay, 32 years. And then the half-life is 8. And if we do 32 divided by 8, we get 4 half-lives. Okay, so we know that 4 half-lives occur during that time. Again, if you want to look at it a different way, you could say you're trying to get to 32, 8 and 8 is 16, and 8 is 24, and 8 is 32, and you know that you've done it 4 times, right? Either way that works for you. Okay, let's see what else we can do here. We've done the number of half-lives, so what would our half-life fraction be? In this case, we've done 4, so all we're going to do is 4 halves. Okay, times 1/2 times 1/2 equals 1 over 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, so at this point, we're at 1/16 of whatever we started with. So how much would remain? We're going to take what we started with and multiply by that fraction. And this time, we started with 100, and then we have 1/16 of it left. And if you calculate that out, that is 6.25 grams, because we started with 100. Okay, all right, so there also is another way to do this once you find the number of half-lives. And I'm going to go over that now because some students find this easier. Okay, let's go back to the last problem and we'll do both this way. Okay, so in this problem, let's say we've worked to the point where we know the number of half-lives. And we did that by taking our total time by the half-life time. And we've got 6 divided by 3 is that 2. So we know we've done 2 half-lives. If we're starting with a 50-gram sample, that just means we're going to divide it in half twice. So if we take 50, divide by 2, we're at 25. 25 divided by 2, we're at 12.5. So we've gone 2 half-lives, and that is how much we should have left. And if you look over to the right, you'll see that that's the same. So doing it this way, we still have to figure out that number of half-lives, but then we just divide by 2 the original sample that many times. Okay? Let me click over to the next one. We'll do it really quickly and then call it a day. Let's see. If the half-life of 100 grams is 8 years, how much will remain in 32? We figured out that you take your total time, okay, and you're going to divide it by that half-life time, and you wind up with 4 half-lives. So if we're starting with 100 grams, we're going to have to divide it by 2 4 times. So we're going to do it this way. 100 divided by 2, 50. 50 divided by 2, 25. 25 divided by 2 equals 12.5. And 12.5 divided by 2 equals 6.25. So we've divided by 2 4 times. So if we go over to the slide that I have, you can see that the answers agree. So whichever way you like, I'm just going to have a few problems today, and then we'll call it a day. I hope you have a great day. Tomorrow we're going to have a short quiz assessment, and then you'll be all ready for spring break. I hope you have a wonderful break.